GRPO, or Group Relative Policy Optimization, is the core reinforcement learning algorithm behind the DeepSeek innovation, and the reason why they were allegedly able to train a reasoning model at a fraction of the cost normally incurred by OpenAI. And now it's starting to get adopted by other LLM providers like Qwen. Now, GRPO itself is just a tweak to existing algorithms like OpenAI's PPO, but it was built on a rich history of reinforcement learning research, and that's why it might seem hard to digest at first. My goal here is to provide you with enough context so that you can understand what all the fuss is about, and also to be able to tweak those annoying hyperparameters needed when using the GRPO trainer. So we're going to get started by understanding where GRPO fits into the larger LLM training pipeline. So we start with a randomly initialized model that just outputs gibberish. Then we pre-train it by predicting the next token on the entirety of the internet. Implicitly, the space model ends up acquiring a lot of world knowledge, but it's not quite usable yet as an assistant because it just finishes your sentence and builds on top of it. To make it more conversational, we run instruction fine-tuning using instruction response pairs. At this point, we've exhausted the entirety of the internet and potentially our budget for human label data as well. So in order to make further improvements, we'll have to be more creative with the type of data that we use. This is where reinforcement learning comes in. It helps us train models without explicit reference answers and use implicit signals instead. One such type of signal is human preference. You might be familiar with this ChatGPT interface where it asks you to choose between two alternative responses. OpenAI's goal here is to gather user preferences and fine-tune their models in a way that better aligns with them. This process is generally called preference fine-tuning, and there are multiple implementations. Notably, OpenAI introduced RLHF, or Reinforcement Learning with Human Feedback. This is quite an elaborate method that requires training an additional reward model, which can predict human preferences. And the core training algorithm that updates the model weights based on the human preference is called PPO, or Proximal Policy Optimization. The reason why I'm mentioning this implementation detail is because GRPO, which is the topic of this video, is a successor of PPO. And I will occasionally reference PPO here, but if you want to dive deeper, check out my previous video. A more recent and computationally efficient alternative to RLHF is DPO, or Direct Preference Optimization. We don't know if OpenAI switched to DPO, but the open source community has definitely embraced it. To learn how DPO works, check out my other video on Tulu 3, an open source model that uses it. So that was preference fine-tuning. But there's another type of implicit signal that we can leverage to make LLMs even better. There's a special class of problems called reasoning tasks, which includes math, computer science, logic, and so on. As opposed to more creative tasks, there's usually one right answer and a deterministic way of figuring out whether the model was correct. So we can harness this binary correctness signal for reasoning fine-tuning. Under the umbrella of reasoning fine-tuning, you'll hear about the RLVR algorithm, or reinforcement learning with verifiable rewards. It's likely that OpenAI has been using something similar to RLVR for a while, at least since their first reasoning model o1, which they announced back in September 2024. But DeepSeek brought it more prominently to our attention when their open source R1 model turned out to be a serious competitor that was allegedly trained much more cheaply. At its core, RLVR also needs an algorithm that updates the model weights based on the correctness signal. For this purpose, we could use OpenAI's PPO, which we already encountered in the context of RLHF, or DeepSeek's GRPO, which is a much more efficient alternative. So hopefully this gives you an idea of where GRPO fits into the LLM training pipeline. It should be clear by now that GRPO sits at the core of reinforcement learning. So I'll spend the next chapter talking about core building blocks of reinforcement learning, but if you're already familiar with these concepts, or if you watched my previous PPO video, feel free to skip it. Reinforcement learning is much more intuitive in the physical world, where we have an agent like a Roomba navigating an environment like your living room with the goal of sweeping the entire surface. At each time step t, the agent takes an action A index t, like moving one foot to the right, which takes it to a new state, S index t. This could be a new XY position, or the agent could get stuck under your desk. The environment can also communicate a reward, R index T, which reflects how much progress the robot made towards sweeping the entirety of the living room. Finally, the trajectory tau consists of all the states the agent visited and all the actions it performed during one episode, or one cleaning session in this case. In the language world, the agent is an LLM like Llama, and the environment is the world external to the LLM, including humans, datasets, and tools like a Python interpreter. To discuss what the actions and states are, we'll walk together through a math question, which we would use for reasoning fine-tuning. Let's take, for instance, this middle school math problem for which 72 is the correct answer. When passing the question to the model, we can use heuristics to deterministically verify that its answer, 72, matches our reference answer. When asking this math question, I basically set the agent to its initial state as 0, which consists of my prompt. And the agent took its first action A0 and predicted the token 2. The environment updated the state to S1 in order to reflect this newly predicted token, and the agent proceeded with action A1, which was to predict the token find. And the environment added it to the state. The model's next action was to predict out, and you get the point. This continues until the agent predicts the end token and concludes the episode. So these were the states and actions, but what about the rewards? Well, given how we design our task, we can only judge the response quality at the very end of the response. The environment can use some heuristics to pull out the final answer, which is 72, and then compare it against the ground truth, which is also 72. And since the model was right, it will get a positive reward. I'm choosing here a reward of 1, but you could set it to any positive value instead. And you can also be more creative with the reward. For instance, DeepSeek's scores the model response not just on correctness, but also on formatting. So to recap, for our particular setup, all intermediate rewards are 0 except for the very last one. But there are cases where people use external reward models to provide intermediate rewards at the end of each sentence in the response. Okay, so the big picture is the agent takes a series of actions and navigates a series of states and receives a reward at the end of the episode. But here's the tricky bit. Somehow, based on this single numeric value, we need to backpropagate through the entire trajectory and through the model and update the weights in a way that reinforces good actions. This is incredibly difficult, and the reason why reinforcement learning has been an active area of research for decades. So let's revisit our state S2 to talk about what exactly happens during one training step. But first, just a little terminology. The LLM is also known as the policy of the agent and is denoted by pi index theta, where theta are the model parameters. This is just a new name for the same LLM we've been using so far. So the agent uses its policy to produce a probability distribution over the next actions given the current state. This is simply saying we're passing the instruction and the tokens generated so far to the LLM, which gives us a probability for each next token in the vocabulary. And since the token out has high probability, it ends up being sampled. Let's zoom into the probability distribution output by our policy. Given that we eventually get a positive reward for the full response, we know the action of predicting out was good or at least not disastrous. So after one training step, we want to increase the probability that our policy will assign to the token out in the state to find, and slightly decrease the probability of all other tokens. Both GRPO and PPO are part of a family of reinforcement learning algorithms called policy gradient methods. They achieve the desired effect of increasing the probability of the token out, given by pi theta of A2 conditioned on state 2, by following the policy gradient. And let's visualize what that means. Of course, our policy has billions of parameters, which we can't visualize as humans. So for simplicity, let's assume our policy only had 2 parameters, theta 1 and theta 2. So we'll plot the output of the policy pi theta only in terms of these 2. Let's also assume that the policy space is this nice Gaussian surface. So when we initialize the policy parameters, we basically pick a point in this space. Here, my toy initial parameter values are 0.5 and -1. So the goal of one training step is to move this ball closer to the peak of the mountain. And policy gradient methods are simply doing gradient ascent on the policy surface. They do so by first calculating the gradient, which is this black arrow, and taking a step in that direction. Here, I actually took multiple steps just to confirm we would eventually reach the peak. Formally, this is how we update the model weights by going in the direction of the gradient. Just a few notes here. First of all, we sum over all the time steps, or all tokens in the response. Second, we take the logarithm of the policy probability just because it's mathematically more convenient, but this will still pull the ball in the same direction. And third, note that I'm also multiplying the gradient by the reward of the final response, which I'm going to write as upper caps R. So when the reward is positive, we go up the mountain. When it's 0, we just don't make an update. And when it's negative, we go down the mountain, or shrink the probability. To be consistent with the policy gradient expressions that you might find in books, I wanted to come back to the reward. For a math problem, we only have a single final reward for the entire model episode. But more generally, we could have intermediate rewards if the environment used some sort of reward model to score at a sentence or even token level. So then, for each action, we could calculate something called the return, denoted by G index T, which is simply the sum of future rewards. For example, the return for action T minus 2 is the sum of the two rewards RT minus 2 plus RT minus 1. It's also common to add a discount factor gamma. This is a hyperparameter between 0 and 1 whose purpose is to exponentially reduce the impact of future rewards. So when calculating the return of one action, the longer ahead we look into the future, the less credit we take for rewards that are further away. So if we substitute GT in our policy gradient update, we basically reconstructed reinforce, which is the very first policy gradient method that was published back in 1992. This is the precursor of modern algorithms like GRPO and PPO. One variation of the reinforce algorithm is to subtract a baseline from the return. So what's the baseline for? Well, let me put it this way. Let's say the agent's goal is to become the richest person on Earth, and say that it succeeds, hence it gets a positive reward. The question is, how good was the last action, AT minus 1? How much partial credit should we give it for the agent achieving this goal? Well, if the agent starts off in the shoes of Jeff Bezos, then it'll have some work to do, but it doesn't feel impossible. However, if the agent starts in my shoes, then that action, AT minus 1, is starting to look like black magic. My action is a lot more meaningful than the current day Jeff Bezos is. So the baseline, or the place where we start from, matters a lot when judging the merit of the action that we took. And various algorithms estimate this baseline in various ways. There's a whole family of algorithms called Actor-Critic Methods, which also includes PPO, that estimate the baseline using a state value function, denoted by V index phi. This is a separate model from the policy LLM, which comes with its own trainable weights. In this context, the policy is also known as the actor because it enacts or it takes actions. And this state value function is known as the critic because it's constantly evaluating the states the agent goes through. Adding a critic brings a lot of computational overhead. First, because the critic is probably initialized from a big model like an LLM, so it's doubling the memory requirements, but also the computational resources because now we need to train an additional model. But the biggest disadvantage, in my opinion, is the cognitive load for practitioners. In other words, these algorithms are just harder to understand. Here's, for instance, an excerpt from a paper that rewrites this delta in terms of all future state values. To dig deeper, you can check out my PPO video. By the way, this delta is also known as the advantage and is denoted by upper caps A index T. After many years in which actor-critic models were very fashionable, GRPO goes back to the basics and adopts a very simple baseline. In fact, it even stops computing different advantages for each time step. Instead of a per-step return, it just uses the final reward. And instead of a per-state baseline, it just uses the same baseline across all time steps, which we'll call B. This might look like a massive oversimplification, but I personally think it makes a lot of sense in the language domain where we don't usually get intermediate rewards, or if we do, they come from reward models, which are inaccurate anyway. In contrast, when you think of video games, we're constantly getting feedback from the environment, be it being punched in the face or getting a gold medal or whatever. But in the lack of intermediate rewards, our intermediate estimations of advantages and value states and so on are probably wrong anyway. So GRPO is just embracing this reality. Let's see how GRPO computes the baseline B for a given instruction. Here, we're looking at the full trajectory generated by the agent in response to the instruction. To compute a baseline for the reward, GRPO samples an additional group of trajectories, somewhere between 4 and 8, and collects their rewards. So the baseline is simply the average reward of this group. To rewrite this consistently with the paper, the advantage is the final reward minus the mean reward of the group, but we also divide by the standard deviation of the group, which is a common way to normalize values in statistics. Now it should be clear why this method is called group relative policy optimization. Okay, so GRPO makes a lot of simplifying assumptions. But to be fair, researchers at DeepSeek did run experiments with intermediate rewards. Given a model response, they used heuristics to separate it into reasoning steps. Roughly, a reasoning step might correspond to a sentence, so we have 7 reasoning steps here. Then, they added a reward model to the environment, which provides intermediate rewards for each of these steps. They call this process supervision. Note, that has nothing to do with supervised learning. It's just a confusing name for intermediate rewards for each sentence in the response. The difference is, at each time step t, we'll use the reward for the reasoning step that t is part of. So for instance, all these tokens in April, Natalia, and so on, all use the reward of the second reasoning step. And when it comes to the baseline, the mean is over all reasoning steps in all groups. So are the intermediate rewards worth it? This figure compares outcome supervision in yellow, which means a single final reward, against process supervision in blue, which has intermediate rewards. We're seeing a little bit of delta here on the GSM-8K dataset, which is a middle school math questions dataset. But if you ask me, no, these small gains don't justify the overhead. It seems like the recurring theme in the GRPO research is just keep it simple. Now let's talk about the GRPO loss. Making our way backwards from the gradient, the loss would look like this. I'll call it LPG for policy gradient. This loss is fine. After all, this is what the original reinforced algorithm used, but throughout the years, we've made a series of improvements. And the reason why we didn't settle for this expression is a perpetual problem in reinforcement learning called variance. Variance happens when the model updates are too large, and we're basically reading too much into some noisy aspect of the data. If we're not careful with these updates, the model can degenerate into a state that it can't recover from. Here, if we allow the probability of the token out to go all the way up to 1, it means we'll never be able to predict anything else in this state. One way to deal with variance is to constrain the model updates. Some algorithms define a trusted region for these updates. Here, their effect would be that the ball would not be allowed to leave this parameter within a single update. This idea was introduced by TRPO, or Trusted Region Policy Optimization, which defined this area using second-order derivatives. PPO adopted the same idea, but implemented it via clipping. Since GRPO builds on top of the PPO loss, let's first discuss how the PPO loss diverges from the traditional policy gradient loss in order to constrain model updates. PPO looks at the ratio between the new model parameters, so after the training step, and the old ones, before the training step. We'll denote this ratio by r and x theta. A ratio of 1 would mean the before and after parameters are identical. So PPO constrains this ratio between 1 minus epsilon and 1 plus epsilon, where epsilon is a hyperparameter between 0 and 1. So the PPO loss replaces the log probability with the ratio between the probability before and after the update, clipped within this interval. Well, almost. PPO actually takes the minimum between the unclipped versus clipped ratio times the advantage. So why is this minimum necessary? Let's break down what happens when the advantage is positive versus when it's negative. Remember, a positive advantage means that the action we took was good and we want to reinforce it. When the ratio r is higher than 1, it means the new probability assigned to the action is higher than the older probability, so the gradient is moving in the right direction, or the direction that agrees with the reward. Conversely, a negative advantage means that the action we took was bad and we want to penalize it. When the ratio is lower than 1, the new assigned probability is lower than the older probability, so the direction of the gradient would indeed penalize the action. These regions where the advantage and ratio agree with each other are the regions we do want to clip to protect against overzealous updates that might be reading too much into the specifics of the trajectory that we're currently training on. On the other hand, there will be cases where the ratio disagrees with the advantage on whether the action should be reinforced or penalized. This can happen due to noise or imperfect estimation. So in case of disagreement, where the gradient is already going in the wrong direction, we actually do want to penalize it as much as possible. And this is where the unclipped ratio does take effect. The reason why we spend so much time talking about the PPO loss is because the GRPO loss uses it directly and simply subtracts an extra term. This term references two policies, the one that we're currently optimizing, pi theta, and the reference policy. The reference policy is different from the denominator of the PPO ratio, where we had pi old. In contrast, pi ref refers to the state of the model before we started the reasoning fine-tuning stage altogether. So for our original pipeline, that would be our preference fine-tuned model. GRPO takes the KL divergence between the current and the reference policy, which is a sort of distance measure between the two distributions. So not only are we keeping the model close to its state before the current training step via clipping, but also close to its original state via this extra loss term. Intuitively, this is needed to compensate for the many GRPO oversimplifications, like removing the state value function, which introduce more variance compared to PPO. Putting this together, here's what PPO and GRPO do during one training step. Our agent, currently in state ST, will use its policy to produce a probability distribution over actions and then sample an action AT. The environment might give it a reward RT. Depending on the circumstance, this might be the intermediate reward or the reward at the end of the episode. PPO passes the agent state through a value function and then calculates the advantage and finally the loss. GRPO samples a group of trajectories and uses their mean reward as a baseline to compute the advantage. Then it calculates the PPO loss and adds an extra regularization term. Both algorithms will then do gradient ascent with their respective losses and update the policy of the agent. So that was GRPO in a nutshell. I know the math can look heavy, but at its core, the algorithm is quite simple. And if there's one idea I want you to take from this is that research papers can be a little bit like Instagram. There's subtle ways to flex, and Greek symbols are one of them. And I'm not just blaming DeepSeek. Any machine learning engineer or researcher has to play the game in order to get published. But once you see past that, these papers become a lot easier to digest. If this helped make things clearer or if it made them more confusing, I want to know in the comments either way. And if you want to keep building your intuition on reinforcement learning, check out my previous PPO video. I'll see you next time.